Control and estimation theory is everywhere, from home appliances to aircraft, and from miniature robots to the Hubble telescope and kilometer-long particle accelerators. My name is Pantelis Opasakis, and I will be teaching you control and estimation theory. Let me give you a quick outline of what we will be discussing and what you can do with control and estimation. First of all, we can model dynamical systems. We can derive mathematical equations that describe the evolution of certain variables of interest in time. We can then use these mathematical equations to simulate dynamical systems using computer software. Most engineering systems come equipped with multiple sensors. For example, a mobile phone comes with accelerometers and gyroscopes, a thermometer, and perhaps a pressure sensor. All these provide measurements of physical quantities, but at the same time are corrupted by noise. Our job there is to filter out that noise. And engineering systems are expected to operate in highly uncertain environments, where almost nothing can be assumed to be constant. We need then to use information from sensors to estimate several unknown parameters as the system operates. This way, we will make our designs reliable, resilient, and fault-tolerant. We can use control and estimation theory to analyze systems, that is, to tell whether they are indeed safe, reliable, and stand up to certain performance requirements. And we can design systems that have such favorable characteristics. But most importantly, we can provide guarantees that our designs are absolutely safe and reliable and robust and resilient. So this is why it's worth studying control and estimation theory. Because it's everywhere. You can find it across all branches of engineering, in medicine, biology, economics, and many other disciplines. There are even naturally occurring feedback loops, naturally occurring control systems, several thereof, such as the one that regulates our body temperature, heartbeat, and blood glucose level. Control and estimation theory offers a new abstract way of thinking for addressing practical problems. You will be exposed to multiple mathematical methodologies and approaches that you can reuse in other disciplines. For example, you will learn probability theory that you will be able to use in machine learning. And you will be exposed to multiple algorithms for solving applied problems. Control and estimation theory lies at the intersection of engineering, mathematics, and computer science. It is by nature a multidisciplinary field of study. A lot can be said about success stories of control and estimation theory. We have, for example, driverless vehicles, have robots that have conquered the world of manufacturing. Exoskeletons that can help people walk. rockets that can take off and land, automated farming, and new ways to harvest energy. Unfortunately, there are quite a few failure stories to report. People are concerned especially about the dangers of autonomous driving.
Video showing what happened just moments before that deadly Uber crash involving a self-driving car. ABC's Diane Macedo has the story.
This dashcam video shows the horrifying seconds before a self-driving Uber hit and killed a pedestrian in Arizona. Tempe police released 2 videos Wednesday. One filming outside the car shows 49-year-old Elaine Herzberg crossing the road with her bicycle. It pauses just before the moment of impact.
Some of these failure stories involve fatal accidents. In other cases, very expensive equipment has been destroyed. But the take-home message is that it is very important to design systems that are safe and reliable. In this module, we will learn 3 things: model predictive control, optimal estimation, and numerical optimization. Model predictive control is like a game of chess. When our turn comes to play, we think of a sequence of actions. We think of a sequence of moves that will maximize the impact that we will affect on the opponent. And we have a model that allows us to predict how the opponent will play. Then from that sequence of control actions, from that sequence of moves, we're allowed to play the first move. And then we wait for the opponent to play, we observe their move, and then again we make a new plan. So we plan and we act, and we plan and we act. This is what is known as model predictive control. In engineering, what we do is that we measure the state of a system and we plan a sequence of control actions, a sequence of future control actions that optimizes a performance index. Then we can apply the first element of that control action. We apply it to the system responds, and then we measure the new state again, and we plan and we act. In doing so, we have to take care so that the safety requirements and the safety constraints of the system are respected. Model predictive control is the bee's knees of modern control theory. It can be used to control linear and non-linear systems, systems with multiple inputs and multiple outputs, hybrid systems that involve switches, large-scale and very complex dynamical systems. The second thing we'll learn is optimal estimation. Given a set of measurements, what is the best we can infer, what is the best we can make out of those measurements, which are, of course, in practice, noisy. Take, for example, the case of a spacecraft that needs to travel to the moon. We have obtained a set of measurements of its possible position, but its actual trajectory is unknown. Optimal estimation can be used to produce an estimated trajectory. When you use GPS on your phone, there is an estimator inside that processes the measurements from the satellite as well as other measurements to provide to you accurate and reliable measurements or reliable estimates of your position. Both model predictive control and optimal estimation rely on optimization. Optimization problems require numerical algorithms to be solved, and these algorithms need to be fast, need to be simple, and have low memory requirements so that they can run on embedded devices, on simple embedded devices. So this is the third thing we will learn. We'll learn a few algorithms that will allow us to solve such optimization problems. So that's everything for now. Thank you very much for watching, and until next time, goodbye.